So if you've ever taken a calculus class, you've definitely seen this symbol, d/dx, the derivative. But what is it really? It is so much more than just some formula you have to memorize. Think of it as the engine of calculus, a powerful tool designed to answer one fundamental question: how fast is something changing right now?
Think about it like this. Imagine a huge water tank, and it's draining out. Now, we could easily figure out the average rate it's draining over, say, 10 minutes. That's simple enough. But what if we need to know the speed of that water loss at the exact single instant the clock hits 10 minutes? Not a second before, not a second after. For that kind of precision, we're going to need a special kind of mathematical engine.
And that engine? Well, that's the derivative. It's the tool that lets us zoom in on one single moment in time and measure its rate of change with absolute, perfect precision. And here it is formally. The derivative, which we write as f prime of x, is a function whose entire job, its whole purpose, is to look at another function, like one for volume or position, and tell us its instantaneous rate of change at any single point you want. Now, what's so cool about this is just how versatile this one idea is. I mean, look at this. In physics, if you've got a function for an object's position, its derivative is its velocity. Simple as that. Take the derivative of that velocity function, and bam, you get its acceleration. In engineering, if a function describes the volume of water in a tank, its derivative tells you the rate of flow. It's one concept with just a ton of different applications.
So let's circle back to our draining tank and actually put this engine to work. We've got the concept down. Now let's go get a real, concrete answer.
Okay, here's our setup. The volume, V, at any given time t is described by this function right here. The question is asking for the rate of draining specifically at the 10-minute mark. And that phrase, rate of, that's our cue. It's basically shouting at us, find the derivative.
And the process for solving this is it's beautifully logical. First, we have to understand the request. See the word rate, know that means we need the derivative v prime of t. Step 2, we differentiate the function. Now, this one's a little complex. It's a function inside of another function. So we're going to use a technique called the chain rule to get the job done. And then finally, step 3, we solve. We just plug our specific time, t equals 10, into that new derivative function we just found.
And there it is. At exactly 10 minutes, the tank is draining at a rate of 187.5 gallons per minute.
But hold on. What about that negative sign? Is that a mistake? No way. It's actually the most important part of the answer. In the language of calculus, a negative rate means the original quantity, in this case, volume, is decreasing. The math just perfectly describes the reality of what's happening to that draining tank. It's fantastic.
All right, let's take this same engine and apply it to a completely different scenario. We're going to shift from fluid dynamics to physics, but as you'll see, the core idea, the process, stays exactly the same.
So here we have a function, s of t, that tells us a particle's position over time. The big question is, when does it actually stop moving? Well, think about it. What does it mean to stop? It means your velocity is 0. And what's velocity? Well, we just learned. It's the derivative of position.
So the process is exactly the same. First, find the derivative of that position function. That gives us this new function for velocity, v of t. Second, to figure out when the particle stops, we just set that velocity function equal to 0 and solve for t. And the math tells us something pretty interesting. This particle actually comes to a complete stop at 2 different moments, at 2 seconds and then again at 6 seconds.
Now for part 2 of the problem, and this is a classic spot where derivatives are absolutely essential. What's the total distance the particle traveled in 8 seconds? It's a really common trap to just calculate the position at 8 seconds and call it a day. But because we know the particle stopped at t equals 2 and t equals 6, it probably changed direction. So we have to break the journey into 3 legs, from 0 to 2 seconds, from 2 to 6 seconds, and finally from 6 to 8. We calculate the distance for each little part of the journey, and then we add them all up.
And when we add those segments together, 32 plus 32 plus 32, we get the true total distance the particle traveled, 96 meters.
All right, for our last example, let's switch gears one more time. We've done engineering, we've done physics. Now, let's see how this same engine of change helps drive decision-making in the world of economics.
In economics, there's this really important concept called marginal cost, and it is, quite literally, just the derivative of the total cost function. It's an incredibly powerful idea that helps a company estimate how much it's going to cost to produce just one more item. So let's imagine this is our company's cost function. To find the marginal cost, we just take the derivative, c prime of x. Now, let's say we're currently making 20 items, and we want to know, hey, is it worth making one more? Well, we just plug 20 into our new derivative function.
And the result? $12.
And this is the powerful insight right here. That $12 doesn't represent the cost of the 20th item we already made. Nope. It's a fantastic approximation for the cost of making the next one, the 21st item. The derivative gives us this forward-looking tool for making smart business decisions.
So, okay, we've looked at draining tanks, moving particles, and production costs. What's the big idea connecting all of these? Well, it's a fundamental shift in perspective.
You see, on one side, you have these functions that describe a static quantity. How much volume is there? Where is the particle? What's the total cost? The derivative acts like a transformer. It takes each of those and turns it into a function that describes a rate of change, the flow rate, the velocity, the cost of just one more.
And that is the crucial point. The derivative is basically a translator. It takes the language of what is and translates it into the dynamic language of how fast it's changing. It lets us move from just knowing a fact to truly understanding the process of how that fact is becoming something else.
Which really just leaves us with one final thought. The derivative is this amazing tool for analyzing change in any system you can describe with a function. So, as you go about your day, what systems are you a part of? What rates of change are happening all around you that, maybe with the right engine, you could start to measure and really understand?